This conference will now be recorded.
Good evening, one and all. This is Rajesh. In our embedded system design under Unit 3, embedded firmware, we will discuss about embedded firmware design approach as well as develop language. So, you know what is an embedded system? Embedded system is a unique system. It is a combination of hardware and software, and the system is designed for doing a specific task. So, embedded system consists of an hardware part and software part. The software part is called a firmware, which is stored in the memory, and based upon the firmware control algorithm written in the memory, your embedded system hardware core along with its peripherals, ICs, sensors and actuators, it does a specific task. So this is our definition. It is a electromechanical system designed to perform a specific function, and it is a combination of hardware and software. So this embedded system is designed to run on its own without human intervention and may be required to respond events in real time. So these are some examples of embedded system as discussed in every class. These are a traffic light controller, metro station, washing machine, DVD player, smart watches, smartphones, electronic toy. Your embedded system can be an independent system or it can be a part of a large system. Coming to elements of embedded system, your system core is connected to your input ports and output ports, to which this input port is connected to a sensor, this output port is connected to an actuator, this system core is connected to your memory, and data is read from the memory. This memory consists of control algorithm, which is read by the system core, and it will behave as per the logic written in the control algorithm, and that logic is written in a high level language or an assembly language. If you are using a high level language, in order to compile it, you require a compiler, and for which you require an IDE. If it is an assembly language, you require an assembler, because a compiler or assembler will in turn convert your high level or assembly language into a machine code, and this machine code is understandable by the processor. So embedded firmware refers to the control algorithm or the configuration settings that the developer develops in order to perform the execution of your embedded system. And we are having two languages, embedded C, C++, and assembly language. So these are the system components: a reset circuit, a brownout protection circuit, oscillator unit, real-time clock, watchdog timer, which are available as part of your PCB. And they are doing the task of doing a reset work or initializing the contents. So how you approach to your embedded firmware is, there are two approaches. Your embedded firmware can be designed by using a super loop based approach, where each task is written in a while loop, and the program instructions are executed task by task. So you are configuring all the common parameters and perform initialization of various hardware components, and each task is executed step by step. So because we are using a C program example, main within braces all configuration and initialization settings, under while we are written all the tasks. So it does not require an operating system for, because there is no task scheduling done here, so we don't require any operating system for our super loop based approach. And non real time in execution behavior, and as the number of tasks increases, the frequency at which a task gets CPU time for execution also increases. So as you are writing a big code, more tasks will be there and more time the CPU has to allocate. So this is the drawback. If you go for the second approach called embedded firmware design approach, we can use a real-time OS or a general purpose OS. But if you use a real time OS, there is a kernel which does task scheduling and priority. So our topic is embedded firmware development languages, assembly language or high level language, or mixture of assembly language and high level languages. So first method is embedded firmware development languages. Assembly language is a human readable notation of machine language. Machine language is a processor understandable language. Machine language is represented in binary form, and your assembly language written for processor will not work for another. Assembly language programming is the process of writing specific machine code in mnemonic form. So instead of binary notations, here the same binary notations are combined such that each processor or control has some instruction set in which mnemonics are developed, where a move instruction will just move the contents on the right side to the left side. So assembly language programming is the process of writing the processor specific machine code in mnemonic form. Converting this into processor instructions is done by an assembler. So the language consists of coding such that it has an operand comma opcode. Opcode tells opcode comma operand, opcode comma operand. Opcode tells what the processor has to do. Operands are the data or the information required to perform the action. So what are the action to be performed for which? So if you see the 8051 assembly instruction move a comma hash 30, 30 is the contents operand to be transferred to the register A. So move A is an opcode, 30 is an operand. If you convert this into binary form, this is the 8-bit binary value which is representing the opcode move A, and then this is another 8-bit which is representing the operand 30. So assembly language is written one per line, and the machine code program consists of a sequence of assembly languages where each statement contains a mnemonic. So if you see the format of assembly languages, there will be a label, opcode, operand, and comments. So a label is an identifier used in order to reduce the reliable on programmers for remembering where data or code is located. Label is commonly used for representing a memory location, address of program, subroutine, code portion, etc. The maximum length of a label differs between assemblers. Assemblers insist strict formats for labeling. Labels are always suffixed by a colon and begin with the valid characters. And these labels contains alpha numeric character underscore and numbers from 0 to 9. So if you see a program in which we have written a label delay, move R0 comma hash 255, and we are written in the next line, we are dumping the contents of 255 into R1. In the next line, we have written decrement R1 and loop till R1 becomes 0. So return to the calling program. Next is assembly language. If you write your assembly language, that assembly language must be converted to an hex file, and that is done by an assembler. Assembly language file is called .asm file or .src file, or a format supported by the assembler. Similar to C and other assembly high-level languages, it is possible to have multiple source files and which are converted by your macro assemblers into object files with the help of a library files. These object files are finally converted to a hex files. So each source file can be assembled separately to examine the syntax errors and incorrect assembly instructions. Assembling of each source file generates a corresponding object file. The object file does not contain the absolute address of where the code is generated. The software program called linker is responsible for assigning absolute address to the object files during the linking process. The absolute object file created from the object files corresponding to different source codes contain information about the address where each instruction needs to be placed in the code memory. So a source utility called object to hex file converter translates object file to the corresponding hex file. So the advantages is efficient code memory and data memory usage. The developer is well aware of the target processor architecture. So if you are using an assembly language, it is the efficient code memory and data memory, because the developer is well aware of the target processor architecture. He knows how to organize the memory, and for better operations we can optimize the code. But this leads to less utilization of code memory and also the data memory. High performance, as optimized code only improves the code memory usage, but it also improves the total system performance. So through effective assembly coding, optimum performance can be achieved for a target processor. Low level hardware access, most of the code written for low level programming, like accessing external devices from the OS kernel, device drivers, and low level interrupt routines, are making use of direct assembly coding. So code reversing, it is a process of understanding the technology behind a product by extracting the information from the finalized product. It can be easily converted to an assembly code using a disassembler program. And what are the drawbacks? High development time. The developer takes a lot of time. He has to understand the architecture, memory organization, addressing modes, instruction set. More lines of assembly code is required. Developer dependencies. So each developer has a freedom to develop and to write the program, and non-portable. So program written for one processor cannot be used for another processor. So next we'll see our embedded firmware development language, where we are mixing assembly language with high-level languages. So embedded firmware development may require mixing of assembly language with high-level language, or mixing high-level with assembly language. Interrupt handling source code is already available in high-level languages. Assembly language, etc. are examples. High-level language and low-level language can be mixed in three methods. First one is you have to mix assembly language with high-level language. Next, you have to mix high-level language with C, like assembly language, or you can use the inline assembly. The passing of parameters and return values between the high level and low level language is a cross compiler. See, if you go for a high level language, we require a compiler. If you go for an assembly language, you require a assembler. But when you are mixing the languages, you require an cross compiler. So mixing assembly language with high level language like C. So assembly routines are mixed with C in situations where the entire program is written in C and the cross compiler is in use, do not have built in support for implementing certain features like ISR. If the programmer wants to take advantage of the speed and optimized code offered by the machine code generated by handwritten assembly rather than cross-compiler generated machine code, writing the hardware peripheral access routine in a processor control specific assembly language and invoking it from the C is the most important advised method. Mixing C and assembly is a little complicated. The programmer must be aware of how to pass parameters from the C routine. Passing parameters to the assembly routine and returning values from the assembly routine to the caller C function, and the method of invoking the assembly routine from the C code is cross-compiler dependent. And the second method is mixing high-level language like C and assembly language. The source code is already written in assembly language, and only the routine is written in a high-level language needs to be included to the existing code. The entire source code is planned in assembly code for various reasons like optimized code, optimal performance, efficient code memory utilization, and proven expertise in handling the assembly. The functions written in C use parameter passing to the function and return values to do the calling functions. The programmer must be aware of how parameters are passed to the function and how values returned from the function and how function is invoked from the assembly language environment. So passing parameter to the function and returning values from the function using CPU registers, stack memory, and mixed memory its implementation is cross-compiler dependent. And in inline assembly is another technique for inserting the target processor specific assembly instructions at any location of source code written in high-level language. So if you want to insert high-level language in a assembly language in a high-level language, you can use an inline assembly which avoids delay in calling the assembly routine from a C code. And special keywords are used to indicate the start and end of the assembly instructions. Hash pragma.asm move a comma hash 31 h hash pragma.nsm. So keel C51 uses the keywords like hash pragma asm or pragma end asm to indicate a block of code written in an assembly. So if you want to write a block of code in the assembly, you can use this method. So coming to our embedded development languages, you can use high level C++ or assembly language, or you can mix high level in an assembly language. The first method is we want to mix assembly language with a high level language like C. So we have written entire program in the high level language and the subroutines are written in assembly language, whereas mixing high level with C language means the entire program is written in assembly language and only subroutines are written in high level language, or depending on the requirement, inline assembly can be used where a portion of the code written in high level language is included in an assembly language. So this is the regarding embedded firmware development languages. So with this, I conclude my topic.